All right, cool. Yeah, thank you very much. Yeah. Yeah, thanks for showing up. Yeah, yeah. It's a pleasure to be speaking in front of so many RL theorists at an RL theory workshop about a paper that's not about RL theory. Initially, this was put in the applications session, but I was like, okay, Dave, please, there's no applications in this one. I mean, I challenge you to find any application in these slides. This is but hopefully it's still about something that you will appreciate, because there's a lot of familiar things that you will know about, like Markov decision processes, Markov chains, dynamic programming, and so on, Bellman equations, and the like.
And you're not applying these to solve a problem?
No, absolutely not, absolutely not. Or well, I mean, maybe I'm going to hint at some applications. I actually wanted to thank Phil for pointing out this representation learning application as an important connection to the practice of reinforcement learning, I suppose. I'm going to say a word about that at the end of this talk. Right. Okay. So my name is Gergely, and this is joint work with my friends from Pompeu Fabra University in Barcelona, specifically with Sergio, Anders, Ludovic, who's here, and Javi. All right. Let's do this. So how many of you have heard about bisimulations before? Not counting Phil's talk. Wow, okay, that's pretty cool. Yeah, there are a few people. All right, okay, so this talk is about the following problem. How do I compare stochastic processes? How do I say that one Markov chain is closer to a Markov chain in an appropriate sense? So if I look at these realizations from like a bunch of different random walks, Markov chains, how do I quantify the fact that these two things on the left are sort of more similar to each other than to those other things on the right, or these things in the bottom? How do I quantify this? How do I calculate the sort of distance that is going to enable me to quantify similarity between stochastic processes? So in particular, I'm going to tell you how this figure was produced, right? So this is sort of based on computing pairwise distances between a bunch of different Markov chains and then embedding them in a 2D space and resulting in some kind of like an intuitive comparison between processes. So I'm going to tell you what this distance is, and hopefully by the end of this talk, you're going to appreciate what this is about. All right, so this is the outline of the talk. I'm going to give you two different definitions of distances between Markov chains, distances between stochastic processes, namely bisimulation metrics and optimal transport distances. So the title of this talk is Bisimulation metrics are optimal transport distances and can be computed efficiently. So first I'm going to give you these definitions. I'm going to give you a perhaps surprising equivalence result between the two of these formulations. I'm going to go relatively quickly on this one, and then I'm going to focus mostly on the second half, which I think is the most interesting bit, which is the computational result, telling you how such things can be calculated via linear programming and a method that is potentially familiar to some of you from optimal transport that's called Synchron's algorithm. And then we're going to close with some more pretty pictures thanks to the 15-minute extension that was afforded to me by the organizers. Hopefully that's going to be worth your time. All right, okay, so in order to define the problem, I'm going to give you some formulas first. So I'm going to study two Markov chains denoted by mx and my. So Markov chain is given as a tuple of its state space, its transition kernel, and its initial state. So m of x is given by x, the state space, px, the transition kernel, and x0, the initial state. So I'm just going to assume that the initial state is fixed and there's no randomness in there. And what I want to calculate is a sort of distance between these. But in order to define distances between the Markov chains, the stochastic processes, I'm going to need some way to define a distance or a similarity notion between states themselves, right? Because before I compare stochastic processes or distributions or families of distributions over objects, I would need to define distances between the objects themselves. And this is going to be captured by something that I'm called the ground cost function, which maps pairs of states, x and y, to real numbers, let's say positive real numbers. So for example, if both state spaces are d-dimensional Euclidean space, this can be just the Euclidean distance if you want, or LP distance, or anything that works in a Euclidean space. Another important example to think of is when I'm given a labeling function that is going to classify states into different categories and then have a cost that is going to check whether the two labels are the same or different, right? So these can be labeling states in a maze, for example, like doorway, reward, initial state, water, whatever you want to capture in your problem. And then the cost would be checking if the states, the pairs of states that you're checking are of the same type or not. So this is another example. Or another one that is relevant to applications in reinforcement learning is, for example, when you're given also a reward function over the two Markov chains, right? So when you're talking about the Markov reward process. And in this case, a way to differentiate between states would be simply just to take the difference between the rewards of x and y. Right? So this would be comparing the states in terms of how rewarding they are. All right. So one way to define distances and similarities between Markov chains is a notion of bisimulation. So bisimulation originally is a concept that comes from theoretical computer science as a way of comparing two different processes. For example, this is something that comes from formal verification. Just imagine that, for example, that you have two different implementations of the same algorithm, right? What you want to check if these two algorithms are producing the same sequence of outputs given the same input, right? So you don't necessarily want to compare these two processes in terms of what they are doing in memory or what sort of operations they do in the internal implementation. What you want to check is whether or not they are producing the same outputs, right? The same sequence of outputs if they are initialized under the same conditions. So this is the origin of the concept of bisimulation. And roughly speaking, you say that one process bisimulates the other, or two processes bisimulate each other if they start from, or you say that two states are bisimilar if they have the same labels, and if the states that they transition to are also bisimilar to each other. So it's some kind of like a fixed point type of definition. So I just wanted to cut some corners and give you here an extension of this bisimilarity relation, which is a real valued extension, which is going to give you like a quantifiable way of comparing two processes. So the distance notion, that is bisimilarity metric, between the two processes is given by this function u star of x, which is written as follows. So I'm going to take a function f that comes from a certain family of logical expressions that are evaluated over sequences of states. And I evaluate this on chain mx, and I compare the result of what I get if I evaluate the same logical expression or the same grammar on Markov chain my. And if this and if these expressions evaluate to the same thing for every single function in a family of logical expressions, then I say that these two processes are close. So all this is to say that this is a very complicated definition that comes from model logic, right? It took me forever to digest what this actually means, and you don't need to exactly understand what this means. I guess what I want to convey here is that this is something that is extremely involved, that is expressed in terms that I guess most of us are not very familiar with. It's expressed in language of model logic. The bottom line, which is the most interesting for this talk, I suppose, is that this metric, this u star, this can be given as a solution of a fixed point equation that looks as follows. So u star evaluated at a pair of states x and y can be written as the ground cost evaluated at x and y plus gamma times, which is a discount factor-like object, times an infimum over the couplings of the next two states, where this infimum is taken over probability distributions that have the marginal distribution that correspond to the transition function of the first chain, and the y marginal distribution corresponds to the transition function of the y chain. So this is essentially an optimal transport distance between the next state distributions with a cost that corresponds to u star. If you squint hard at this, then you can realize that this looks an awful lot like the Bauman equations, the Bauman optimality equations for a certain Markov decision process, where the action space is this set of couplings of next state distributions. So this has been an interesting journey for this literature to get from the original logic-based definition to this fixed point-based definition. It took them about 20 years to reach this conclusion. And this is a result that is mostly well known in this bisimulation literature, which is people working in logic, DCS, and so on. So something that is possibly a little bit more familiar for people that work in machine learning and machine learning theory is the concept of optimal transport distances between probability distributions. So and this is the main topic of my talk. So this is a concept that originates from probability theory and mathematics, and this establishes a notion of distance between two stochastic processes that is defined as follows. So I'm going to consider pi, which is a coupling between the two stochastic processes. So this is essentially a joint distribution of the two stochastic processes such that its x marginal corresponds to the x chain and its y marginal corresponds to the y chain, right? But you allow them to use the same random points, essentially. You allow them to couple together their transitions. So pi is such a coupling. So what you do is that you simulate xt and yt, the sequences from this coupling. You evaluate the costs along these coupled trajectories, c, xt, yt, and then you simply take their discounted total sum, right? So you say that two trajectories are similar to each other if their total discounted cumulative costs are low, right? So this is how you compare two realizations of trajectories. And you say that the two stochastic processes are small if you can find a coupling that is going to make this very small on expectation with respect to the coupling, right? So you just couple together the two processes, and then you find the coupling that makes this distance as small as possible. So this is a similar this is a very popular notion of distance that has been gaining traction in machine learning these days. I would say that it's not very well studied in the specific context of learning distances between stochastic processes. Yeah. Right. So. Right. So the thing. Right. So that's exactly the point that I'm getting at, right? So that there's this notion of bisimilarity, right, which comes from this convoluted logical definition, modal logic. I don't know, very philosophical and very complicated, right? And turns out that after 20 years of progress, this community has realized that this definition can be equivalently written in terms of a fixed point equation. In this optimal transport definition, right? So just look at this expression, and then you can almost immediately see that this distance is a solution of the same fixed point equation as before, right? So you see that this definition that I just gave, which is based on optimal transport and coupling together trajectories and so on, this solves the same type of fixed point equation simply because it is a sequential decision-making problem, right? That satisfies the Bauman equations in an appropriate sense. So this is one of the observations that we made in this paper, and this is kind of like a newly discovered bisimulation relationship between these two distance notions. So there's a huge community of people that have been studying bisimulation as a similarity notion, coming from TCS and logic and all of that. And turns out that what they have been studying all along was an optimal transfer distance, right? Which can be phrased in terms of probability theory as opposed to logic and all of that. There's a small difference is that this notion of optimal transport, this works for general costs, right? Whereas bisimulation only works in terms of labels and in terms of functional expressions that are expressed in terms of those labels. So, oh yeah. Uh-huh. Right, yeah, sorry, I did not say that. Yeah. So these couplings that I'm taking the infim over, these are so-called causal couplings, which means that they sort of respect the arrow of time, right? They respect the direction of time. So you're not allowed to couple together future events with past events. So you're not able to say that something that plays a sequence forward and something that plays the same sequence in reverse. You don't want to say that these are similar, right? You only want to allow the couplings to couple to get the randomness forward, right? Right. Right. Yes. Right. So basically, you can apply all of fundamental MDP theory here, and notice that that actually you don't need to consider all causal couplings. You don't need to consider all couplings that are based on historical information. It's enough to look at Markovian couplings, and then from that you can derive this fixed point equation kind of expression. Right. Yeah. Thank you for asking that. Yeah. Mm-hmm.
You are still saying that they are different, right? Because there is something in the future. I would like
Right.
to turn the past rather than the future.
Right. Yeah. So there's a whole discussion to be had about like what is an appropriate way in which I can compare Markov processes. And one first idea that one may have is that, okay, I'm going to say that two Markov processes are similar if their stationary distributions are similar, right? So for example, if they generate the same stationary distribution, you want to say that they are similar. Right. I would say that this is, in a certain sense, a more sensible definition, because just imagine the following two Markov chains. There's two states, right? One just deterministically flips back and forth between 0 and 1, right? So just goes back and forth like this. And the other one is just a sequence of IID coin flips, right? Both of these have the same stationary distribution, right? But they are very different, right? So they are not, they're really not the same Markov chain, right? So this distance notion is able to distinguish these processes in a meaningful way, right? And that is, I would say, like a little bit more relevant if you want to use this for downstream applications, for example, like representation learning or something. Yeah, right. So here you use discounting for the same mathematical reasons as in reinforcement learning or in MDP. Yeah, because that doesn't give you like a single number, right? So the question is, okay, how do I aggregate those individual distances between the transition kernels, right? So what Phil was suggesting that maybe one can just look at the optimal transport distances between the individual next state distributions, right, in terms of the costs, and then just call it a day like that, right? But then this is going to give you like a bunch of similarity distances between the states, but it doesn't give me like a sense of how similar the actual Markov chains are, right? It's just going to give me like a collection of distances, but I wanna get like one final answer to my question: how similar are these chains? Right. Okay. So this is the notion that we are studying in this paper. So if you just accept this as a meaningful definition, which I hope you do, but let's just accept it for a second. We can talk about its legitimacy later in the break. Or maybe if you have more questions at the end of the talk. But I want to talk a little bit more about like the actual computational results that we have in the paper, which is about answering this question. Okay, how the hell do I compute a solution for this fixed point equation? So one idea that you may have is that, well, okay, so let me just define a Bellman operator, which is just using the right-hand side of these fixed point equations as an assignment operator, and let me try to find a fixed point for this in a value iteration-like way, right? Let me just iterate or repeatedly apply this operator to an initial guess of the value function v and hope that this is going to converge to a fixed point. We know that this is a contractive operator and this is going to converge. So in principle, this may look like a reasonable idea, but okay, there is one tiny drawing that is not showing up, unfortunately, that was like a very ominous picture of a skeleton that is somehow like implying that this is like a deadly bad idea. You're going to descend into your grave if you try to do that. yeah, it has horrible consequences. So the problem is that if you want to go down this way, right, then applying this dynamic programming operator is horrendously expensive. This is really expensive because you have to calculate that infimum, right? You need to calculate that coupling of minimal cost between two distributions with given marginals, which means that you need to solve an optimal transport problem. for every single application of the Bellman operator. Even worse, you need to solve as many optimal transport problems as many state pairs you have in the two Markov chains. For every pair of states, you would need to calculate such an infimum, and that is just prohibitively expensive, right? You don't want to do that. That has like cost of x times y to the 4 or something like that. So that is not something that you would want to do. Even approximately, this is going to be very expensive. So let's see what else can we do. Because we managed to find something that's, I think, a lot more elegant of a solution to this problem than doing this. So our approach is based on solving, like reformulating this whole problem as a linear program in a finite dimensional space, right? So it's sort of obvious to write our original optimization problem as an infinite dimensional linear program in the space of trajectory distributions. That is, of course, like not something that you would want to do again because of the infinite dimensional nature of that problem. But turns out that you can project down that infinite dimensional optimization problem into this finite dimensional linear program. So this is saying the following: that the distance that I want to calculate between the two chains is going to be a minimum of a linear function. So my variable is going to be denoted by mu. I'm going to give it a name sometime very soon. So I'm going to look at the minimum of mu times c. C is the ground cost, subject to some constraints. So this mu needs to satisfy the following 3 constraints. The first is, right, so you need to think of this mu as essentially the joint distribution of xt, yt, and xt plus 1, yt plus 1 under a coupling of the two processes, right? So this is the joint distribution of 2 consecutive state pairs. And they need to satisfy the respective assumptions. So the first of these is like a flow condition, which says that whatever mass flows outside of a certain pair of states should be the same mass as what flows out, right? This is a flow condition, or sometimes called a detailed balance condition for those of you that come from statistical physics. The second of these is saying that these joint distributions should behave like joint distributions, so that they should respect the marginal constraints, right? So that if I look at the joint distribution of xy, x prime, y prime, that should be the same as the probability that I'm in xy and y prime, and then I move over from x to x prime, so that they should respect the dynamics of the 2 original chains, and the same thing for the y constraints as well. So just rephrase everything into this linear program, right? Which I guess right now it doesn't look like that much of an improvement over what we've been doing so far. But I'm going to show you that this is something that results in some pretty practical algorithms at the end of the day. Right. So I'm going to call these objects, maybe this is how I should have started with this. So I'm going to call these objects occupancy couplings, right? So this occupancy coupling, this mu of x, y, x prime, y prime, this is going to be the discounted sum of probabilities that my coupled processes are going to visit x, y, and x prime, y prime in round t and t plus 1, right? And these are discounted by gamma to the t. So this is like the discounted number of times that I'm going to visit these states on expectation. So this is a kind of extension of the concept of an occupancy measure from Markov decision process theory. And you can see that every such occupancy coupling, so every such joint distribution, also induces a conditional distribution as well that you can get just by marginalizing out. So this pi of mu, this is something that you can think of as a policy if you want, right? So this pi of mu, so this is the probability that I'm going to move over to x prime, y prime, given that I'm in x, y. And this is really just like the what I can calculate via base rule from mu. So every mu induces such a transition coupling, but of course every transition coupling induces an occupancy coupling as well. If I execute the transition coupling, that induces like a coupling over the 2 processes, which have an associated mu as well. So this is the usual relation between policies and occupancy measures in Markov decision processes. So once I have these, I'm already afraid of how that picture is going to turn out, but maybe it's not going to show up. So with this concept, I'm going to define my algorithm, my algorithmic template as follows. So how many of you know about the Synchron's algorithm for calculating optimal transport distances? Okay, so a few people. So we're going to do the following. So this is a mirror descent-like algorithm. So so we're going to be working in the space of occupancy couplings. We're going to calculate the sequence of occupancy couplings as follows. In each round, what I'm going to do is that I'm going to try to find a coupling such that I minimize mu times c, my linear objective. And I also have a penalty for moving too far away from my previous occupancy coupling. And this penalty is defined in terms of, well, this distance notion between occupancy couplings. It's called a conditional relative entropy. So it's some specific distance notion whose identity is not super important for this talk. But importantly, the coupling that I'm going to calculate, the set of mu's that I'm optimizing over, this is going to be not the set of all couplings, because like projection to that complicated set, which is the intersection of B and Sx and Sy, that's a very complicated set. So what I'm going to do is I'm going to alternatingly project to the intersection of B and Sx and the intersection of B and Sy. So this is an idea that comes from optimal transport. Synchron's algorithm essentially does this. You alternatingly satisfy one half of the constraints and then the other half of the constraints. Let's see if I have a picture. Okay, I don't have a picture, but the way that this so what was supposed to show up on the picture is that, well, you have essentially like two sets, right? You have like one set who you want to project to. This is like the set of x marginals and the y marginals, and then you alternatingly project to one of the sets, and then you project back to the other one. Just go back and forth between projecting to the two sets until you eventually converge to the intersection of the two sets. So this is essentially an analysis and an algorithmic idea that is based on alternating Bregman projections to two sets. And somehow the hope is that these alternating projections are going to be easier to calculate and easier to work with than projections to the entire set. Right, I know that this sounds a little bit abstract, and this is the question that it leads to. Okay, and how do I perform projections to these two sets? How do I perform projections to I guess Bx means the intersection of the first two, and By refers to the intersection of the second one. So how the hell do I calculate these projections is the big question. And this is where my, yeah, sorry. Right, yeah, so I had very poor understanding of this. I know that this is an accepted fact in the community of optimal transport, and there were some very complicated mathematical papers that established this fact. Now, having worked on this paper, I understand that this is something that can be shown by an application of the usual mirror descent analysis. So somehow, by a clever application of convex analysis, you can show that this happens. And this was observed like early on in the 1960s by Richard Synchron, who came up with this as a heuristic algorithm of just using these alternating projections to calculate couplings. And he observed that this is something that converges actually linearly towards the intersection. So basically, the more and more you apply these updates, you actually do make progress towards the intersection, which is non-trivial. Right. Okay. So what we managed to show, which I think is the nicest algorithmic result, or like the nicest result that does lead to an algorithm in this paper, which is inspired by the theory of entropy regularized Markov decision processes. So it says the following: that this primal form of updates that I've just specified in terms of occupancy couplings, this is something that can be expressed in an equivalent dual form that is expressed only in terms of policies and value functions. So in terms that we are very convenient as reinforcement learning theorists working with, right? So here, policies correspond to what I call transition couplings, pi, and value functions are, well, I guess value functions. So what we show is that the primal form can be written in this very convenient dual form, where pi k plus 1, so the occupancy coupling corresponding to mu k plus 1, is essentially an exponential weights update done to the previous transition coupling, the previous policy, where you perform the exponential weight update on the y distribution and then you make sure that your x marginal is the true marginal that you want to respect, right? So this is the x projection. So there's this multiplicative p x prime given x to make sure that your distribution over the x is fixed, and then you renormalize with respect to y, right? So that's what that first line means. This is a so-called Synchron update, which is really just a renormalization of the columns of the transition, of the joint transition matrix. So that's what the first update does. It's actually a very simple computational step that you can do very easily. After this, you calculate an update to the value function, and that is really the question, like what should be the value function for this update to actually realize a projection to the feasible set. And turns out that in order to calculate the value functions, what I need to do is solve this fixed point equation over here, which again may look a little bit convoluted with all this like log sum x and all these and all these complicated functions, but this is essentially just a Bellman operator. This is essentially just like a nonlinear version of the usual, or like this is like a regularized version of the usual Bellman operator that says that Vk for any state where xy and x prime is written as a softmax, or I guess this is more like a soft min, with respect to this distribution, and this is essentially the right-hand side of the Bellman equation, right? It's like immediate cost plus gamma times future expected value. So this is something that we call the Bellman Synchron equations, and we refer to the resulting algorithm as Synchron value iteration. It's really just a combination of these two ideas, Synchron's algorithm and value iteration. So it just works as follows. We define the Bellman operators Tx of phi and Ty of phi, depending on whether we are doing an x projection or a y projection. And then we simply try to find its fixed point. So the right-hand side of this is Tx of phi, right? Tx of phi k. And this fixed point equation is Vk equals Tx of phi k Vk. So we define these Bellman operators, and then we run the following algorithm. That we just perform a sequence of steps. In each round, we apply this Bellman Synchron operator a bunch of times to our previous value function estimate. Then we calculate the Q function, and then we calculate the policy update, and then we just keep on looping through this whole thing. So here, the way that I've stated this algorithm is that we are applying these Bellman operators m times. So we don't necessarily find a fixed point in this implementation. We only apply the operators a small number of times. And you can ask, okay, but is that good enough? Or like, does this make a difference? And well, it turns out that we did some experiments, and turns out that the choice of this m parameter does not matter at all. Like, you converge essentially as quickly towards the optimum as if you found the fixed point exactly. Yeah. Right, so I'm going to show you our theoretical result, right, which is this, which only works for m equals infinity for now. So we don't have any theory for a smaller m at the moment, or, well, no correct theory. I got the draft, which does not work. But it essentially says the following, that this algorithm does converge to an optimal solution of this optimum transport problem. It gives you an estimate of the optimal value function and an optimal transition coupling in this many steps. So essentially like 1 over epsilon squared steps, you find an epsilon optimal solution. And of course, for this, you need to tune the parameter eta, which is the only tuning parameter of this method. And essentially, the proof of this result is based on like a sort of like fancy version of the mirror descent analysis. So you perform a regret analysis for mirror descent, and then you combine this with an analysis of the constraint violations that come from the fact that you're doing alternating projections, right? That in not every round do you actually play feasible points, so you're violating the constraints all the time, right? But turns out that the cumulative constraint violations add up in a reasonable way that you still get a convergence rate towards an optimal transport plan. All right. So does this work? Is this fast? Is this a good algorithm? So it turns out that this algorithm is actually about at least 10 times faster than the naive algorithm that I mentioned as an option earlier on, right? That is based on repeatedly solving the optimal transport problems in every state pairs. So what we have is like significantly faster, and this is what demonstrates that this is a much more viable idea out there, or a much more viable idea than what other people have been playing around with so far. So this is kind of convincing. Right, so let me show you some pretty pictures in the remaining time that I have. So, so this methodology allows us to calculate now distances between Markov chains, as I promised. And you can ask a variety of different questions. So here, one thing that we studied is that, okay, we generate a bunch of MDPs and a bunch of Markov chains, and we want to get an understanding of how similar these Markov chains are to each other. So we generated a bunch of these 4 rooms environments with different initial states and different reward distributions, and then we calculated pairwise distances between the Markov chains, and then we plotted them on this 2-dimensional map. And for example, what you see here is that here these points correspond to environment that have this type of structure, that the initial state is next to a doorway, and the reward or the closest reward is one doorway ahead of you and in a corner, right? So this environment is similar to that environment because you need to perform the same steps in order to reach a reward, right? So you see the same distribution of rewards from these initial states, right? And you see that the symmetries are respected. So if I take the same environment, I rotate it, then I'm going to get the 0 distance between the two processes. And if I see like an initial state that is right next to the reward, that is going to get me a different distance. Yeah. Right. So we just calculated pairwise distances, and then we just embedded this in a 2-dimensional space by multidimensional scaling. So this is really just some kind of an embedding of the metric. Right, so here it's defined in terms of labels. Like we have a label which is a separate label for a doorway, a separate label for just a regular square, and a separate label for whether or not there is a reward. And then the cost function is whether or not the 2 labels are different from each other. So it's a very simple cost function that you're working with. So this is really just to illustrate that this gives you like a meaningful way to compare different environments and different Markov chains that are working in those environments. Yes, we got some more distances right here. Yeah, I can explain that later because I think I'm running out of time, even though Dave is not here, so he's not here to. Oh, is he? Oh, you're. Okay, so I hope that. Okay, anyhow, okay, I'm too afraid. So what I'm going to show you here is. So this method actually gives you also couplings between Markov chains. So not only distances, but it gives you a way of calculating minimal distance couplings between chains. And for example, what I'm showing here is that here I have like one environment on the left, which is like a small dimensional Markov chain of just 9 states, and a sort of like higher dimensional Markov chain on the right-hand side, which is 4 different rooms, right? And I'm just considering random walks in both of these environments. Then I'm looking at couplings of them, again with the same type of cost function, which is just defined in terms of labels. So you see that this coupling works in a way that respects the symmetries, right? So that these little robots, these little agents are moving together or tracking each other's movement in a way that respects symmetries. So there's this interesting moment that I really like, and actually that is not a hack. This is like truly an optimal coupling that we have calculated. This is not just a made-up video. So there's this moment where you approach the doorway on the right-hand side. The other guy sticks to the wall and then starts tracking the movements of the right random walk by flipping the symmetries one more time, right? So there is a certain symmetry that is respected as you're on the left-hand side, right? You see that they move together. I think that this is very satisfying to look at, actually. There's this moment where you flip over to the other side, and then you start respecting another kind of symmetry as well. Yeah, and again, like we didn't play around with this all that much. This is really just an optimal coupling. Right, and then getting back to this initial figure that I showed, this was produced in essentially the same way. So this is just a family of random walks on the interval 0 to 10, right? the labels correspond to nothing happening or sticking to the upper wall or the lower wall. It's the same label. And under this labeling function, this shows that these two random walks on the top, they are similar. They are embedded into those two little dots. These two are also similar in terms of being close to each other on this plot. And the structure that have emerged from these experiments is that here along these axes, so these dots, the difference between them is the initial state in where the Markov chain starts from. So that is this axis, and this axis corresponds to the probability of going up. Right? So you know, we didn't do like any cooking or any magic, and this structure just emerged from, again, just calculating pairwise distances and embedding everything into this two-dimensional space, which I think is, again, kind of satisfying. So this is just the distance matrix of the same experiment defined between the different random walks that we have run, and the couplings between the trajectories. So you see that up on the in the upper line, you see that those are at a very low distance, and the couplings, they move together in a very nice symmetric way. One more time. And as you consider larger and larger distances, for example, like these yellow dots, they correspond to couplings that do not really move together all that much. You cannot really couple together those Markov chains in a very satisfying way that they move in an intuitive way close to each other. Right. There's another plot. Can anybody guess what this is? So this is the album cover of Coil from beautiful ambient record from 1995 that I highly recommend, and it has nothing to do with the talk whatsoever. Okay, no. Sorry, conclusions. Yeah. Sorry, that was an accident. Yeah. So we have some other results in the paper. We have another algorithm that's even easier to implement and even nicer to run. And what I'm particularly excited about is the applications of this. Like, how do you use this methodology or these optimal transport distances to define distance metrics or similarities between Markov chains? And how do you use that, for example, for representation learning, as Phil was saying, right? So just imagine that you have like a high-dimensional Markov chain, like a perceptual stream or whatever, right? And then you have a bunch of small-dimensional representations that you want to consider, right? And you want to say that, okay, I want the representation that is closest in terms of optimal transport distance to the high-dimensional one, right? And one really curious fact about our solution is that since it is written as an LP, it is actually differentiable with respect to the transition function and the representation, which I think may turn out to be important for applications in representation learning. There are many open questions as well. So like right now, these algorithms that we have are sort of dynamic programming algorithms. They require knowledge of the transition functions, and they require like perfect policy evaluation steps. And right now, running these algorithms are is kind of expensive. So we are looking at other potential ways of calculating these optimal transport distances. For example, by using stochastic optimization methods for solving linear problems and stuff. All right, okay, so this is the end. Thank you very much. So I'm not sure about that application for calculating couplings. One application that may be relevant is estimating the mixing time of Markov processes, because the mixing time can be upper bounded in terms of couplings, and minimal distance couplings correspond to like exact estimates of the mixing time. But I think like nobody in particular knows how to calculate an optimal coupling. Like what people do there is usually just get like a heuristic, right? Right. Right. Yeah. So like most couplings, or like most coupling-based estimates of important quantities, as far as I know, are done just by heuristics or just by designing a coupling by hand and just hoping and praying to God that this is going to be like close enough to optimal. But this method gives you a way of like actually computing minimal distance couplings. Well, I mean, sort of, you see that all of this stuff that I was talking about, maybe I was very effective at hiding that, but these are really for the tabular setting, right? Because these updates, they do require you to know P, right? Like the policy update that you see over there. And in principle, you can always plug in like an empirical estimate, but you know, God knows if that's going to work or not, right? Or how well that is going to do. But again, since our distance notion is written as an LP, right? You can do like stochastic primal dual methods for solving that instead of doing this kind of Synchron nonsense that I was describing, right? So, and hopefully those stochastic optimization methods would not need access to distributions. And this is similar to what is happening in optimal transport, right? In optimal transport, there are these Synchron style methods that do need you to know the distributions, right? But there's stochastic optimization methods that can work with just like a stream of samples. And hopefully we can get there as well. Yeah. Uh-huh. So say again, so just one Markov chain?
Yeah.
Uh-huh, uh-huh. Right, yeah, yeah. Yeah. So then I guess your y variable would just be a constant, right? Yeah, then I don't think that it would be calculating anything interesting at all. But, huh? Uh-huh. Right. So there's like one way in which I can turn this into a meaningful distance notion, or I can consider a version of this for a single Markov chain, and that would be when x and y are the same, except for their initial states, right? So their transition kernel is the same, but they are initialized from different states. So this is one way in which you can sort of compare states within the same Markov chain, and. Uh-huh. Uh-huh. Yeah, I would say so. So there's this kind of like regularized Bellman equations. If you squint hard at this, you're going to see that this is actually the regularized Bellman equations that replace the max with a softmax. So this is sort of a generalization of that. We had like a bunch of results about this in this paper from 2017. Mm-hmm. Mm-hmm. Right. Yeah. I think that would be a fantastic question as well. Yeah. For example, imitational learning, right? So I would want my policy to imitate the expert policy in terms of an optimal transport distance, which is potentially more meaningful than looking at their stationary distributions as what you do in like generative adversarial imitational learning, right? Which is like a very weak notion of similarity. If you want to have like a stronger notion of similarity, right? Yes, that's a very good point. All right, folks, thank you very much.